So, hello and welcome to Optocraft's presentation on this year's CLASS conference on wavefront metrology for contact lens and intraocular lens testing. My name is Christian Brock. I'm with Optocraft since 2014 and I will start this presentation with a few words on the company. We'll then go into details of the refractive power measurement. We'll share some information on the wavefront measurement principles, and then we will see how we do really measure the RGP and soft contact lenses, for example. I will go into share some information on inline measurement, and then we will look at a system which is designed for production applications. So, Optocraft was founded in 2001. We are located in southern Germany and we are ISO 9001 certified. We are currently 29 employees with distributing partners in Asia, in the US and in Israel. And since 2018 we do have a partnership with Micro Epsilon. So we were founded in 2001. This means that this year is our 20th anniversary. We are there since 20 years. What we do is we provide metrology equipment for contact and intraocular lenses. We provide service, support, expertise for the quality of your products and for your production processes. There are systems that focus on the measurement of semi-finished lenses, tools and molds. So we measure the 3D surface shape of such surfaces, and also there are systems for finished lens testing where we measure the light, the transmitted wavefront. These are RGP lenses, autoK lenses, scleral soft contact lenses, spheric toric and multifocals, of course. So here's an overview on the typical parameters that we can measure, and I will share some more detailed information in this on the next slide. You will see this. So basically, what do we measure? We use optical metrology to test optics, and for example, you have a lens that should look like this, but you do not want to look it like this or like that, and this typically is what you detect with the wavefront metrology. So there's one turnkey tabletop instrument, the ophthalmic CTO, which measures the refractive data and the optical quality of your lenses. And in comparison to a traditional lens meter, which does subjective measurements and has a strong operator influence, wavefront metrology does objective measurements with minimal operator influence, which is a very strong point aside from the many different data you get and data reporting. So in addition to that, the wavefront metrology that we are using is based on Schock-Hartmann. It's very fast and it's very stable. So you can just put it on any table, this instrument, and you can do your measurements of your lenses, where you get a very quick and extensive quality check on the refractive data, sphere, cylinder and prism, the power map, add power, where you can measure, and you can measure also the imaging quality, which tells you a lot about the lens you have manufactured and also about your manufacturing process. In addition, the geometric data is measured, like the diameter or the precision of the lens. And here I would like to show you a short video on this CTO. So here you can see how the operator takes an RGP lens and inserts it into the instrument. And as soon as the lens is inserted in the instrument, we get the result, we get the measurement results. So this is just for illustration of the speed that we can achieve with this technology. Okay. So, objective measurements, ISO compliant for contact lens measurement. You have an intuitive software interface and you get a lot of data and data logging out of this, and can also automate the processes. We'll see some more on this later. You can also measure multifocal lenses, where here is an example on a power map that you see on the left side is the 3D power map. On the right hand side you see an average radial profile, where you can clearly identify the different zones in that this multifocal lens has, and you can attribute the refractive power accordingly. So this is just an example of what you get from such wavefront measurements. But beyond refractive data, beyond the power that you get from this measurement, you can, as I mentioned, you get information on the imaging quality. And for this, let me briefly explain the principle of the Jacques-Hartmann. So here we have a lens, which is here called the optical system. So you send light through the lens, the light collects the aberrations of the lens and then comes to the Jacques-Hartmann wavefront sensor, where we do have a microlens array and a camera, and from the local spot displacements we can reconstruct the wavefront. And then on this reconstructed wavefront, basically we run a Zernike analysis where we fit a set of Zernike coefficients, and here are shown a few, like the astigmatism and the coma, and also the spherical aberration. And these single Zernike aberrations, you can connect them to certain types of lenses and certain type of lens shapes. For example, the astigmatism will show you that you have a toric lens, and it will show you the amount of cylinder that you have in your toric lens. Or in case you are manufacturing a spheric lens, and you measure an astigmatism, you will see that you have maybe a molding error. Same for spherical aberration or coma. So either you have these aberrations by design, or there are certain errors that you can connect with these aberrations. And there are not only these aberrations I've shown. There's a whole set of orthonormal coefficients that you can use to analyze your lenses, to analyze and get information on your process. So, for example, here's a measurement of an RGP lens, and on the left-hand side you see the wavefront as measured, including the defocus. Now, if we subtract the defocus is mainly due to the refractive power of the lens. So we can, in the software, we can subtract the defocus and look at the higher order aberrations, and we see that this lens has a certain amount of spherical aberration. Now we go further and look only at the high-level higher order aberrations. So we subtract tilt, defocus, astigmatism, coma, and spherical aberration. And then we can see that these aberrations with higher frequency, we can correlate them to the manufacturing process. On the left-hand side is shown a lens with a good quality, and on the right-hand side you see a lens with a bad quality, and you clearly see these different features in this high-frequency wavefront aberrations. And by this is one example how you can compare good and bad lenses, how you can get information on your manufacturing process. So now there's another video I would like to show where you can see the measurement of 3 different RGP lenses. Again, I take this cover slide, I place the lens on it, and this is the first lens. It's an RGP lens, and now you can look here at this wavefront. As you see, there are no distinct features. It's mainly the same color, so the aberrations are displayed in false color, and there are no strong aberrations in this lens. The second lens does have a certain amount of aberrations. You can see here on the top right a certain feature, so there is some amount of aberrations that we have in this lens. And the third lens that I will measure right now does have a considerable amount of aberrations, so you see clear features. And if you would look in detail at the numbers that the software provides on the wavefront and on the imaging quality, we can also do a quantitative analysis of this quality and of the lens errors. Also, what you can do, there is another video that I would like to show you in addition to the wavefront, in addition to the imaging quality, there is a vision control camera, and the image of that is shown here on the right hand side. So this is a high resolution image of the lens, and now I'm measuring a soft contact lens, a toric soft contact lens, which has a toric mark. And in this high resolution image of the lens, actually we can detect the toric mark. So I need to activate the algorithm that detects this mark by double clicking, and now I have done it. You can see now that the lens position is detected and the toric mark is also detected. Now I deactivate it, I confuse the software a bit, and now I reactivate it, and you see how the pointer switches again to this toric mark. Okay, so in addition to the measurement of the wavefront and of the optical quality, we also get information on the position and of geometric features of the lens, and of course measurement in solution, in saline solution, is also possible. Now, because this wavefront measurement by Schack-Hartmann is quite stable, and it's fast, so we can use this for inline measurements. And basically what we do is we have an illumination unit, we have a detection unit, and we mount that around your production line. Maybe the lenses come in a tray and are moved through the system, and so each lens is measured consecutively. And we have shown in the field that we get really fast cycle times of half a second from lens to lens, for example. So this is possible. This can be automated in a really straightforward way, and this module that we show here is prepared for integration into your production line, basically. So now if we're talking about about the production environment, not only R&D, but so maybe you would want to have a system which is simple to use, and where you do not need a lot of prior knowledge on the process, and which does a lot of sanity checks. So in traditional contact lens measurement, you have up to 5 different steps in order to characterize a lens and to get all the information you need to do your quality assurance. You use tweezers, fingers, tissues. Sometimes you measure in liquid, sometimes in air. These are subjective measurements, and so on. All in all, it's a time-consuming process, and it is difficult to train. So you need you need operators with expert knowledge. Now, we offer a system which is called the SHS ophthalmic omnispec, which unites all these different instruments into one system, to one wavefront measurement device. In addition to the system, to the CITO that I showed before, this has 3 cameras. There's the Schack-Hartmann wavefront sensor, which does the wavefront measurement. There's a vision control camera, which provides the high resolution top view image, and there's in addition a side view camera, which provides a side view of the lens. Yes, and from the side view camera, we can calculate the apex position of the lens and the front contour, and we get also information on the sag. Another very important feature is the open top cuvette shown on the top left side in this slide, which provides an easy loading, so you don't have to fuddle the lens into a small cuvette manually, but you can insert it and the lens just floats into position. And most important, you have saline filtering and a temperature control. So the lens is measured in a really well controlled way, which is quite important if you have many processes around going on. And also the software of the system does several sanity checks to inform the operator that whether the measurement results are valid or not. There's a vibration sensor, for example, and so on. So temperature control. So here I show a little bit of data on the effect of temperature on the lens diameter. So it's the difference between 20 and 35 degree, for example, here for 8 different contact lenses, and you see a clear variation in the diameter when you change the temperature from 20 to 35 degrees. On the sag, there is also a clear influence, as shown here. And at last, here's an example: two lenses, lens 1 and lens 5, and you can also see that there is a difference in the actually in the power profile. So these are multifocal lenses with a certain power difference. Yeah. So here you can see this difference that the temperature affects the geometric properties and also the refractive properties. So the ophthalmic omnispect, as I mentioned, is the core component, is the multifunctional wet cell. There's a pump that continuously pumps the saline solution and makes measurement clean, so to say. Now, what matters to Optocraft? We focus on customer service and on relationship, requirement engineering, installation and training, and service support planning, and so on. We focus on the details of our products in order to make the operator's life easier and to make your quality control more efficient. Multifunctionality, as I mentioned before, is an important topic. So that makes the lens handling easier, the measurement process easier, and you get all the information from one system. And we focus on speed and robustness. Our technology enables us to use our systems in line and to get really fast and speed results. Last but not least, precision and accuracy, and we are happy to do proof of measurement capability in instrument qualification and so on. Okay, so the wavefront metrology provides objective, precise information on the refractive and the geometric data, and additionally information on the imaging quality. And you get objective measurement results, so you can improve your process control. And you can improve your lens designs in R&D, but also wavefront metrology is fast and stable, so it can be used in line. And with this omnispect system and the open top wet cell with temperature control, this improves the stability and the efficiency further. So with this, I would like to thank you for your attention, and in case you have questions, please contact us. Thank you.